Hello friends, today we shall discuss what is continuous charge distribution and types of charge densities and the applications of Gauss law. Here, what is continuous charge distribution? If the magnitude of charge on a body is much more greater than the magnitude of charge on an electron, then the quantization property of charges is ignored and assumed that the charge is continuously distributed on the surface and is called continuous charge distribution. Depending on the nature of charge distribution, the charge densities are classified into three types. They are linear charge density, surface charge density, and volume charge density. The example of continuous charge distribution is similar to density of liquid. When we refer to the density of liquid, we suppose that the liquid is continuous, and here we ignore the molecular configurations. And according to the additivity property of charges, the net charge on a body is equal to the sum of individual charges, that is Q equal to Q1 plus Q2 plus Q3 so on up to Qn. And according to the quantization property of charges, the net charge on a body is equal to an integral multiple of fundamental charge. But these properties are found impractical over continuous charge distribution. Therefore, a charged body is subdivided into small elements, and the surface area of such elements is taken as delta S. The area delta S of the small element is very small in macroscopic level, but it contains a large number of charged particles. And if delta Q is the charge on the surface delta S, then the quantity delta S upon delta Q represents charge density. And there are three types of charge densities. They are linear charge density denoted by lambda, and lambda equal to Q upon L. Thus, linear charge density is the amount of charge per unit length of the conductor. The SI unit of linear charge density is coulomb per meter. Charge on Q is in coulomb and length it is in meter. Therefore, SI unit of linear charge density is coulomb per meter. This implies Q equal to lambda L. Thus, the charge distributed on a body is calculated as Q equal to lambda into L. Here lambda is linear density of charge. And secondly, surface charge density denoted by sigma, and sigma equal to delta Q upon delta S. Here delta Q is the amount of charge on a small element delta S. Thus, surface charge density is the amount of charge on unit surface, and the SI unit of surface charge density is coulomb per meter square. The unit of charge is coulomb, the unit of area is meter square, hence unit of surface charge density is coulomb per meter square. And here delta Q equal to sigma into delta S. Then volume charge density, it is denoted by rho. Volume charge density, it is the amount of charge per unit volume of the conductor. Thus rho equal to delta Q by delta V. The unit of charge is coulomb, the unit of volume is cubic meter. Hence the unit of volume charge density is coulomb per cubic meter. And these surface charge density and linear charge densities are used in the applications of Gauss law. And according to Gauss law, the net charge on a closed body is equal to 1 upon epsilon naught times the net charge enclosed by it. Then applications of Gauss law. Coulomb's law can be applied to calculate the force, electrostatic force between 2-point charges, and it is also used to calculate electric intensity at a point due to a point charge. But Coulomb's law cannot be applied to continuous charge distribution or extended charges. Therefore, the theory of continuous charge distribution is used in the applications of Gauss law. And Gauss law is used to calculate electric intensity at a point due to uniformly charged infinite long straight conductor or wire. It is also used to calculate electric intensity due to uniformly charged infinite plane sheet, and to calculate electric field due to spherical cell, uniformly charged spherical cell. The first application is to find electric field due to uniformly charged infinite long conductor. Consider an uniformly charged conductor of infinite length, and it produces cylindrical electric field around it. To calculate electric field at a point P due to uniformly charged infinite long conductor, we imagine a Gaussian cylinder of length L and radius R. And a cylinder has three surfaces. They are curved surface, the surface area is S1, and upper plane surface of area S2, and bottom plane surface, it is S3. Let phi 1, phi 2, phi 3 be the electric flux through S1, S2 and S3. Then the total flux is equal to the sum of flux through S1, S2 and S3. Therefore, the flux through curved surface phi 1 is equal to E into S1 cos theta. We know that electric flux phi equal to EA cos theta. Here S1 is the surface area, therefore A is replaced by S1. E S1 cos theta. Since the conductor is positively charged, electric field lines are directed away from the conductor, and S1 is the area vector. It is perpendicular at any point on the curved surface. Therefore, the angle between area vector S1 and field vector E1 is 0. That means they are moving along the same direction, or S1 and E are parallel to each other. Therefore, for curved surface, E vector and S1 vector, they are parallel to each other. Hence, phi 1 equal to, if they are parallel to each other, then theta equal to 0. If theta equal to 0, cos 0 equal to 1. Therefore, phi 1 is equal to E into S1. Here, S1 is the surface area of curved surface, nothing but it is the surface area of the cylinder. If L is the length of the cylinder, R is the radius of the cylinder, imaginary cylinder, then S1 is equal to surface area of cylinder is given by 2 pi RL. Thus, ES1 can be written as E into 2 pi RL. Now, the flux through the upper surface S2 is phi 2, and phi 2 is equal to E S2 cos theta. Here, the angle between electric field vector and the area vector is 90 degree. Area vector is directed normal to the outward normal to the surface, and field vector it is horizontal or parallel to the surface. Therefore, angle between E and S2 vector is 90 degree. Therefore, E and S2 they are perpendicular to each other. That means theta equal to 90 degree. If theta equal to 90 degree, cos 90 equal to 0. Therefore, phi 2 equal to 0. Cos 90 equal to 0, then phi 2 that is equal to 0. Then if phi 3 is the flux through bottom surface, for bottom surface area vector S3 it is outward normal, and field vector it is parallel to the surface. Therefore, angle between E vector and S3 vector, area vector is 90 degree. Therefore, phi 3 is also equal to 0, and phi 3 is given by E S3 into cos theta. Here E and electric field vector and area vector S3 they are perpendicular to each other. Hence, theta equal to 90 degree, cos 90 equal to 0. Therefore, phi 3 is also equal to 0. Now, the total flux through the imaginary cylinder is phi E. Electric flux through the imaginary cylinder of length L and radius r is phi e, and phi e equal to phi 1 plus phi 2 plus phi 3. That is equal to phi 1 equal to e into 2 pi r plus phi 2 equal to 0, phi 3 equal to 0, hence phi e equal to e into 2 pi rl. Consider this as equation 1. Now, according to Gauss law, the total electric flux through a closed surface is, according to Gauss law, phi E is equal to Q upon epsilon naught, where Q is the total charge on this cylinder. And here we consider, since the charge is uniformly distributed, that is continuous charge distribution, and for continuous charge distribution, linear charge density is given by lambda equal to Q upon L, the amount of charge per unit length of the conductor. This is unit length of the small length of the conductor, that is lambda equal to Q by L, hence Q equal to lambda into L. Therefore, phi E is equal to lambda L upon epsilon naught. Consider this as equation 2. Equation 1 is phi E equal to E into 2 pi RL, and equation 2 phi equal to lambda L by epsilon naught. Therefore, comparing equation 1 and 2, E into 2 pi RL is equal to lambda L upon epsilon naught. Therefore, electric intensity at any point P at a distance r is E equal to L get cancelled, remaining lambda upon 2 pi r into epsilon naught, or 2 pi epsilon naught into r. This is the expression for electric field due to uniformly charged infinite long conductor, where r is the distance of the point from the conductor. This is r, from the axis of the conductor. And here intensity is inversely proportional to distance. And in case of point charge, electric intensity is inversely proportional to square of the distance. In case of continuous charge distribution, linear charge distribution, electric intensity is inversely proportional to distance of the point. And in case of point charge, intensity is inversely proportional to square of the distance between the point charge and the point. And in case of dipole, electric intensity is inversely proportional to cube of the distance. Therefore, electric intensity at the same point due to uniformly charged long conductor is greater than the electric field due to a point charge, and this is greater than it is greater than electric intensity due to a dipole. Thank you. In next class we shall derive expression for electric field at a point due to uniformly charged infinite plane sheet and electric field due to a spherical charged cell. Thank you.